One really useful tool when you're talking about functions is to be able to visualize them. And one of the ways to visualize a function is to look at its graph. So we're gonna talk about graphing functions in what's known as the Cartesian coordinate system. So here's how the Cartesian coordinate system works. By the way, this is also sometimes called the Cartesian plane or the rectangular coordinate system, right? So it has some different names. It gets its name Cartesian from René Descartes, who was rumored to have sort of dreamed this up when he was laying on a hospital bed and looking at a ceiling, and there was a fly on the ceiling, and he was like, how could I describe the location of the fly? And he thought, well, I could put a grid on the ceiling, and then I could describe its location based on this grid. So it's called the Cartesian coordinate system. But anyway, we imagine a grid with a starting point called the origin. So in this case, this point right here is what we'll call the origin. Right? So it's the place where you have these two lines intersecting, and we call those lines axes. Right? So we have this horizontal axis that we'll call the x-axis, and the vertical axis, which we'll call the y-axis. And the place where they intersect is called the origin. Then we can describe any point in space by its horizontal and vertical distance from the origin. Okay, we describe this point using an ordered pair, x, y, where x is the horizontal distance, or in other words, the distance that you travel along the x-axis, and y is the vertical distance, or in other words, the distance that you travel along the y-axis. Okay? So for example, the point 3, 2 is the point 3 units to the right of and 2 units above the origin, right? So 3, 2, we would go 3 units to the right and 2 units above the origin. So there's the point 3, 2. I'm not sure if I'm actually going to be able to fit all of these points on here, but I'll try. So it says plot the points 2, 6, 3, 0, blah, blah, blah. Well, let's plot the point 2, 6. So this would be the point 2 units to the right and 6 units above, 2, 3, 4, 5, 6 units above the origin. So there's the point 2, 6. 3, 0 would be the point 3 units to the right of and 0 units above the origin. So there's the point 3, 0. 0, 5 would be the point 0 units to the right of the origin and 5 units above it. 1, 2, 3, 4, 5. So there's the point 0, 5. Negative 7, 8. Now, negative 7 indicates that from the origin we're going to move to the left. 7 units. 1, 2, 3, 4, 5, 6, 7. And then a positive 8 means we're going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's negative 7, 8. 7, negative 8 would be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And negative 7, negative 8 would be over to 1, 2, 3, 4, 5, 6, 7, and down. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so hopefully that gives you some idea about how we describe points in the Cartesian coordinate system. Now we use this system to visualize functions by letting x, the input, be the x-coordinate, and by letting f of x, the output, be the y-coordinate. So when we think of our ordered pair x, y, we're going to think of this x as the input of our function, and we're going to think of this y as the output of our function. Okay? So to figure out what a function looks like, we can simply make a table of values and plot the resulting ordered pairs. So let's do that. So let's graph this linear function, f of x equals 3x minus 4. Okay, so what I'm going to do is make a table of values. And then I'm going to have my ordered pair xy. So this is another way to say it would be this is going to be my input, this is going to be my output. Okay, so let's see. Now for your inputs, it's good to choose some negative values, and 0 is usually a good thing to plug in as well, and some positive values. So I might plug in like -3, -2, -1, 0, 1, 2, and 3. Those are usually some good points to plug in. And I'm just going to use my calculator to figure out what the outputs are, right? So if the input's -3, then I'm going to do 3 times -3 minus 4. 3 times -3 minus 4 is -13. When the input's -2, I'm going to do 3 times -2 minus 4. That's -10. And similarly for the rest of them, right? So I'll race you. See if you can finish this before I do. It's quicker if you can do it in your head, right? It's quicker. Anyway, so I've got my inputs, I've got my outputs. So my ordered pair for this row is going to be -3, -13. For this one, it's going to be -2, -10, and so forth. And now I can plot these over here, right? So -3, -13, I think is going to go off my graph paper. I don't think I have, right? So -1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it only goes to 10 really. But we could say 11, 12, 13-ish would be about right there. -2, -10 would put me right there. -1, -7, 1, 2, 3, 4, 5, 6, 7. 0, -4, 4, 1, -1, 2, 2, and 3, 5, 5, right there. Okay. Look at that. Notice that you get this beautiful straight line, and that's because this is a linear function. So I don't have a ruler with me. I wish I did. So if you don't have a ruler, you just kind of have to eyeball it. But that's what the function would look like. Okay, so that's how we visualize. That's kind of how we visualize this function. There are all kinds of things we could point out here, like notice that when we move up 3, we move over 1, right? So that means when our outputs, or when our input increases by 1, our output increases by 3. And it's constant, right? Which is why it's a linear function. It's because it's a straight line, that's where the name linear comes from, right? Because when you graph these things, you get a straight line. Anyway, so kind of cool. Practice some more. Number 2 is not a linear function. It's an exponential function. It says, graph the exponential function, f of x equals 3 times 2 to the x. Okay, well, I'm going to do the same thing that I did before. Okay, so let's see. Oh man, this is going to be kind of weird, I think. But if I plug in -3, I'm going to have 3 times 2 to the -3 power. That's going to be 3/8. So I'm going to say 3/8. If I plug in -2, I'm just going to cheat and come back here and plug in -2. It gives me 3/4. If I plug in -1, I get 3/2. If I plug in 0, if I plug in 1, if I plug in 2, and if I plug in 3, okay, so you can see it starts to grow really quickly. You can also get these as decimals if you want. So if you want to, that might be easier so you know about where to place it. So this is 0.375. This one is 0.75. This one is 1.5. So it might be a little easier for you to graph that way. Anyway, so my ordered pair here is 3 and 3/8. -3, 3/8. -2, 3/4. -1, 3/2, and so forth. 0, 3, 1, 6, 2, 12, 3, 24, which we're not going to get that one on there. But anyway, we can plot these now. So -3 and about 0.375. So 1, 2, 3. 0.375 would be like not quite halfway, right? -2 and 0.75, that's more than halfway. That's 3/4 of the way. So that's about right there, maybe. -1, 1.5 would be right about there, right in the middle between 1 and 2. 0, 3, 1, 2, 3 puts us there. 1, 6, 1, 2, 3, 4, 5, 6 puts us there. So you see it's not a straight line, right? 2, 12, 2, 12. Well, I know that that's 10, so 11, 12 is like whew, somewhere up here. And then 3, 24 is going to be, goodness, it's going to be this distance doubled again. So it's like off the page, right? I don't know. Maybe we can measure it. It's like, yeah, it's a little bit off the page. So by the time you get to 3, you're already off the page. Okay? But what you'll notice is that this never quite goes down to 0. It's never going to reach 0. So I'm going to be very careful when I draw this so that it doesn't cross that axis. Okay? But it kind of looks like that. Okay? That's kind of what that exponential function looks like. So not a straight line. And it gets steeper and steeper and steeper the further out you go. Okay? But that's that one. Let's look at another one. It says graph the quadratic function. Quadratic function. There's a word we haven't seen before. Well, at least not in this class. But you've probably seen the word quadratic in your previous algebra classes. Whether you did or not, let me just tell you, a quadratic function means that you're going to have an x squared, right? And you're not going to have anything bigger than an exponent of 2, right? So you'll have an x squared in there. So that's a quadratic function. Let's see how that works. Okay. Anyway, I'm just getting a bunch of points on there so that I have a decent idea of what this thing looks like. Okay, but let's see. So I'm gonna do. I wonder if I do this, is it gonna get? No, that's not what I want. So, okay. So my advice would be use parentheses. Whenever you have exponents, use parentheses around the number, because we want this thing to come out positive. Because if you multiply -3 times -3, you get a +9. And if I don't put the parentheses around it, it gives me the negative version, which is not what I want. So, okay, so I need -3 squared minus 4. And if I change that out for a -2, if I change it out for a -1, if I change it out for a 0, if I change it out for a +1, if I change it out for a 2, what is going on here? And if I change it out for a 3, I get a 5. Ooh, this is weird. Notice the repeats, right? It kind of feels wrong, but we'll see what pattern this makes. Okay, let's plot these points. -3, 1, 2, 3, 5, 1, 2, 3, 4, 5. -2, 0. Okay, -1, -3, 0, -4, 1, -3, 2, 0. So you see kind of this mirror image almost, and then 3, 1, 2, 3, 5, 1, 2, 3, 4, 5. Well, that's interesting. So you get this kind of, well, it's not a V shape, because if it was a V shape, then we would just have straight lines going from here to there, and you can tell it's kind of going to be a curvy line. So it's more like a U, I guess, more like a U shape, like that. Okay, we call this thing a parabola. It's called a parabola. Anyway, so that's that one. So quadratic functions always end up making parabolas like this. So they're always, they could be upside down, right? If the x squared is a negative, right? They could end up upside down, but they're always parabolas like that. So that's kind of cool. Okay, here's another one. This is back to a linear function, right? So graph the function g of x equals -1/2 x plus 5. But this time we're given explicit instructions. We want it graphed over the domain -2, 6. So we're not going to consider any other inputs, only the inputs between -2 and 6. So here we go. Now, I already know that this function is going to be linear, so I really don't need that many points. In fact, I only need 2 points, because if I have 2 points and I know that it's a straight line, then I can just connect the dots with a straight line, right? But I'm going to plug in a few others. Here's what I'll do. Let me plug in the endpoints, -2 and 6. And then I'll come back and fill in some details if I feel like I need to, okay? Okay. All right, so if I plug in -2, I'm going to have -1/2 times -2 plus 5. And that comes out to 6. If I plug in 6, I'm going to have -1/2 times 6 plus 5. And that comes out to 2. Oh, that's kind of weird, right? But anyway, so I get the point -2, 6, and the point 6, 2. So -2, 6, 2, 3, 4, 5, 6, and then 6, 1, 2, 3, 4, 5, 6, 2. By the way, I should have mentioned this earlier, but if you know of quicker ways to graph these functions without using a computer or a graphing calculator, like if you can graph these functions by hand, but in a different way, you're welcome to use whatever method you like, okay? But if graphing is kind of like new to you and you want to just stick to the charts, then like, yeah, you know, that's totally fine. Anyway, but I know that this is a linear function, so I can just connect the dots with a straight line. How do I know it's a linear function? Because it has the form mx plus k, right? Something times x plus k, so it's a linear function. Anyway, but I could plug in some stuff in between just to make sure. Like if I plug in 0, negative 1/2 times 0 is 0, plus 5 is 5. So I get the point 0, 5. 0, 1, 2, 3, 4, 5. Yeah, it looks like that's on the same straight line, right? Or if I were to plug in like 3, 3 might be bad because I have to multiply by 1/2. So maybe let me plug in 2. If I plug in 2, negative 1/2 times 2 is negative 1. Negative 1 plus 5 is 4. So I get the point 2, 4. 2, 1, 2, 3, 4. Right? Again, it's kind of falling on that same line, same pattern. So, but the thing is, here's what you really need to point out, though, is that you're not going to draw a line going through the whole thing with arrows on both ends because this doesn't extend forever in both directions. It's only between x equals negative 2 and x equals positive 6, right? That we want to graph this thing. So I'm not going to do the arrow thing. I'm just going to say that's it, right? With those dots at the end. So it doesn't extend any further than that. It's just between those two values. Okay? Anyway, so that's how graphing works. Now, there are some things that we can tell looking at the graph of a function. So one thing that we can tell, first of all, is we can tell if what we're looking at is a function at all, right? And we do that using something called the vertical line test. So the reasoning behind the vertical line test is this. You may recall that each input of a function is only allowed to have one output. So when you're looking at the graph, each x-coordinate can only have one y-coordinate associated with it. And consequently, the graph of a function should never have multiple points on the same vertical line. They should never have multiple points kind of stacked on directly on top of each other. And so that's called the vertical line test, right? So for example, we can determine if these graphs represent a function. So this first one does not represent a function, right? Like if I pass a vertical line through this function, notice that it's going to hit the function in more than one place. Let me do this with a pencil, right? So like I can pass a vertical line through the function here, and it only hits one time. But if I pass a vertical line through here, it hits 3 times, right? And so that's a problem. So this is not a function, right? It's not a function. Because it fails the vertical line test, right? VLT, vertical line test. So it fails the vertical line test. What about part B? Part B, we have almost the same scenario, but sort of rotated. Now, if you pass vertical lines through this, here it's only going to hit once. Here it's only going to hit once. Oh, well, here it hits only once. Here it hits only once. And you can kind of tell, sorry, you got to make your lines vertical, but you can kind of tell no matter where you draw your vertical line, it's only going to hit once. So this is a function. Right? It passes the vertical line test. Okay, so that's one nice thing about graphs. You can tell right away just by looking at them whether you've got a function or not. The first one's not a function, this one is. Another thing you can do really easily with functions is you can tell what their domains and ranges are. Okay, so remember the x-coordinates are the inputs, the domain, and the y-coordinates are the outputs, that's the range. So to determine the domain of a function, just imagine its projection onto the x-axis. So just imagine like shining a flashlight on it and seeing what shadow it casts on the x-axis. To determine the range of a function, just imagine its projection onto the y-axis, right? So imagine the shadow it casts onto the y-axis, and that's its range. So I haven't drawn in the functions yet, but let's determine the domain and range of some functions. So let's start with this function here. let's say that you've got a situation like this. Okay, and let's see what its domain and range is. So I'm going to color code this. So with the domain, I'm going to do in green. The domain is the projection of the function onto the x-axis. Okay, so again, if you imagine shining a flashlight on this thing and seeing what shadow it casts on the x-axis, it would look kind of like this, right? It would look like this. So now imagine, so that's your domain, right? So the domain. Let's write the domain in interval notation. Remember, with interval notation, we put the smallest number on the left, the largest number on the right. So the starting point here would be -2, right? -2, x equals -2. The largest number on the right. So we've got 1, 2, 3, 4, 5, 6. Okay? You use parentheses if those numbers are not included. You use brackets if those numbers are included. And they are included here. So we're going to use brackets on both sides. So there's your domain. The range is the projection onto the y-axis. So if you imagine shining a flashlight or kind of squishing the function, pushing it onto the y-axis, what gets covered up? Well, it's going to cover up everything from here to here, right? So that's going to be the range. So the range, again, smallest to largest. So the smallest number is going to start at -1, and then it's going to go up to, so we're going to start at -1, and it's going to go up to 1, 2, 3, 4, 5, 6, 7, 8. So the range is -1 to 8. Okay, let's do another one. So we could have a situation like this. So maybe we've got just like a straight line. Okay. Let's see if we can find the domain and range of that function. So domain. Imagine sort of squishing this onto the x-axis, right? Seeing what shadow it casts on the x-axis. So it would look like this. Right? So the domain here, well, we go smallest number on the left. So that's 1, 2, 3, 4, 5, 6. So -6. Largest number on the right, 1, 2, 3, 4, 5, 6. Ah, +6. What do you know? Okay. Parentheses if the number is not included. Brackets if it is. This left endpoint is not included, so I use parenthesis. This right endpoint is included, so I use a bracket. Right, so there's my domain. What about the range? So the range is the projection onto the y-axis, so it would look like this. Okay. So the range is going to go from -1, 2, 3. So from -3 all the way up to 1, 2, 3, 4, 5, 6, 7. Okay, the -3 is not included. The 7 is. Okay. And one more. Okay, so let's say you've got this kind of situation. Okay, So the domain is the projection onto, and in fact, you know what? Let's say that it extends forever on the left, but ends right there on the right. Okay, so domain is the projection onto the x-axis. So it's going to be from here over. And this thing is going to go on forever and ever in that direction, right? Because it continues on and on. Okay? That's what the arrow indicates. So the domain here is going to be negative infinity to 1, 2, 3, 4, 5. Okay, what about the range? If you squish it onto the y-axis, it's going to cover from here down, and then it's going to go forever and ever and ever. So the range, again, smallest to largest, so you're going to go from negative infinity all the way up to 1, 2, 3, 4, 5, 6, 7, 8. So from negative infinity to 8. Okay, so there would be the domain and range of that function. Okay, it should go without saying that you could have an arrow on the right, in which case you'd have like positive infinities, you know, and stuff. But anyway, that's that. So that's all I have to say about graphing functions.